Okay, welcome everyone. Hao is going to be talking about sewing-factorization theorem and coends. Feel free to start whenever you're ready.
Yeah, uh, I'm already ready, and I'm really uh happy to stand here to give you my talk. And I would like to thank Dr. Chi and Dr. Flor for inviting me to give this talk. And the title of my talk today is called Sewing Factorization Theorem and Coends. And this is based on a joint work with Bingui, and he is also in this Zoom meeting, as you can see. Okay, so before I get into details, I will briefly introduce what is my goal of my talk. So the goal of my talk is to introduce a series of papers based on a joint project with Bingui. And as you can see, there are archive numbers here. And I will call them as GZ1, GZ2, and GZ3. The main result of these three papers is called the sewing and factorization theorem, or SF theorem for simplicity. And we obtain a SF theorem for a finite logarithmic chiral CFT of arbitrary genus. And the goal of my talk today is going to introduce what is SF theorem and explain why it is important to study SF theorem. Uh, since we are going to talk about a finite logarithmic chiral CFT, so throughout my talk, I will fix a C2 cofinite ungraded VOA V, but I will not assume that it is self-due or rational some conditions like that. And I will denote the representation category of V by rep V, just like this. And by Huang-Lepofsky-Zhang, rep V is a braided tensor category, and the tensor product in this tensor category is usually denoted as the fusion product. That is the box times in the latex symbol. Okay, this is my setting, and I want to say something a little different from a vertex operator algebra view. It is something called the coends in the conformal view theory. And in the literature, there are many two ways to study finite logarithmic chiral CFT. The first method is usually studied by VOA community, and they may use pseudo traces and modular S transformation to study this finite logarithmic non-semi-simple CFT. And for the TQFT community or TQFT people, tensor category people, they always use something called coends or ends and their categorical S transformation to study the finite logarithmic chiral CFT. So in this talk, I would like to show that our VOA approach called the sewing-factorization theorem can be related to the method introduced by the TQFT community. And so so to demonstrate my idea, I would like to say something about coends in the beginning of my talk. So the idea of the summing over all intermediate states in physics can be realized by coend construction in a rigorous way. This mathematical realization is introduced by Lyubashenko and formulated by Fuchs and Schweiger in another way. So there is already some literature about the relationship between pseudo traces and coends. And the initial relation between these two things are studied by Gainidinov and Ranko to give a precise formulation of non-semi-simple modular Verlinder formula. Of course, they did not prove their non-semi-simple modular Verlinder formula because their papers are full of conjectures. And it is, in particular, it is conjectured in their paper that their modular S transformation defined by pseudo traces coincides with the categorical S transformation defined by coends. So this is the general story. And I draw a picture about this story like that, like this. So the left-hand side is the VOA side. The right-hand side is the TQFT side. To relate the lower genus conformal block with the higher genus conformal block, VOA people may use the pseudo traces and the modular S transformation defined by pseudo traces. And the TQFT people may use something called coends and the categorical S transformation defined by coends. Our approach is something in the middle, and we just like that. And as we already know that our SF theorem can be related to coends. And in the paper that will appear this year, I will show that our approach can also be related to pseudo traces. So our approach will explain how coends will be related to pseudo traces in quite a natural way. Okay, so in this talk, I will mainly focus on this side, just as the relationship between TQFT community and our results. So I will focus on coends and describe how coends are related to sewing and factorization theorem in a natural way. So to demonstrate my idea, I would like to introduce the definition of the coends. And of course, I will introduce the definition in VOA context. We start with a natural number L and a category D. We choose a bifunctor F, that is a bifunctor from two copies of rep V tensor L to D. And we choose an object D, A in the category D. A family of morphisms from F W conjugate W to A is called dinatural if it is if it is natural with respect to any morphism in this space. The definition is quite simple. If you have a morphism in this space, you will get the following morphism here and here, and we apply the morphism phi W and phi M here, and this diagram will commute, and this is the definition of dinatural. Okay, if a dinatural transformation satisfying some universal property, that is some co-limit condition, then it will be called a coend in the category D. The universal property will ensure that if our coend exists, then it must be unique. And in this case, we may write our coend as an object in D, like this kind of integration formula. And if our category rep is semi-simple, then you can replace the integration by the direct sum. And this is our definition of coend. And if you reverse all arrows in our definition of coend, you will get a definition of the notation called and. And the difference between this notation and this notation is that it is that this W is on the upper side and this W is on the downside. Okay.
Okay,
Uh,
there's a question actually. So, regarding the integration with notation. So, in
uh,
case the category D is semi-simple, then you could both of them are just the summation. Both of the integrals become summation. So this satisfies all the axioms, right?
in fact, if you want to replace this integral by the direct sum, you
Mm-hmm.
have to let this category to be the semi-simple.
Yeah, that's right. Oh, I see. Yeah, so
Yeah, yeah,
there's
yeah,
okay.
yeah. In the case that the VOA itself is is rational, then you can replace this by the direct sum.
So the direct sum is precisely giving you the co-ends and ends in both
Yeah,
cases.
yeah, yeah,
Okay,
yeah,
cool.
yeah, yeah. In this semi-simple case.
Okay, thank you very much.
Okay. Okay, so I will introduce Lioba-Steenker's coends and ends in our VOA context. In this page, I will assume that the VOA is strongly finite. That is, it is C2 cofinite and self-due and some satisfying some minor conditions. And the rep V is rigid. This is a conjecture. Okay, so the Lioba-Steenker's coend is defined by the coend of the bifunctor of the representation category V, just like this. And the dimensional transformation is of the form here. And since we have the rigidity conjecture and we have the self-due condition, we can prove that the L is self-due and is isomorphic to the Lioba-Steenker's coend here. And so L also has dimensional transformation like this. Okay. Actually, Lioba-Steenker proves the existence of the coend in the category sense. And if you want to translate their result to our VOA context, you have to assume the rigidity of the rep V. So in the literature, the Lioba-Steenker's coend, the existence of Lioba-Steenker's coend is guaranteed by the rigidity conjecture. Okay, TQFT people may describe their topological modular functor by some kind of home space involving the coend. By Lioba-Steenker, Fuchs, and Schweiger, they describe the topological modular functor
Wait, how can you hear me? We lost you for a second, I think. We'll wait. Maybe has internet. Oh, there. You're back. Sorry, you froze for a second. So you were just telling us about this hum. Do you mind starting from there? Thank you.
Yeah, I think his volume is. I couldn't hear him actually.
Yeah, it seems to be your mic. Let's test.
Yeah, the microphone does not seem to be working, and yeah.
We can't hear you. I'm sorry. Do you want to try your other audio? I think you were connected with two things, right? Possibly.
Yeah, I had such a situation recently. I mean, Zoom gets freezes very
Strange.
frequently
Yeah.
recently. Yeah.
Yeah. Yeah, and if you have headphones, how? Yeah, we can try those.
let me try
We can
and
hear
Oh,
you
okay.
now. We can
Okay,
hear you
now it's
now.
working.
Yeah,
Now
it's
it's
very
working.
strange. So we can hear you. Great.
Okay, cool.
okay, my AirPods also work, I think.
Wonderful. Can you hear us? Yeah?
Yeah, I can hear you. I can hear you.
Wonderful. Okay, so maybe let's go back to the home. That's where you were when you
Okay,
got cut.
okay.
Okay, thanks.
Yeah. I just mentioned that the home space, they describe the topological modular functor with some kind of home space involving the coend. And in order uh, to make their description more similar to our description, I will choose this kind of home space, but also some kind of home space involving coend. And certainly, they did not start with the vertex operator algebra, and they just describe their topological home modular functor by this home space. So, but I describe their description in terms of a vertex operator algebra context. But as I will show later, their home space is isomorphic to our space of conformal blocks in VOA context. This is one of our main results. Okay, this is our starting point. So in order to describe this sentence, I will introduce the definition of a conformal block. In addition to the VOA data, I would also like to introduce some geometric data. The geometric data is like this thing. We choose an unpointed compact Riemann surface with local coordinates x, and the underlying Riemann surface is denoted as C. It has n marked points, x1 to xn. Each marked point is equipped with a local coordinate eta I. And in our setting, C is possibly disconnected. So this is our setting. And we choose a V tensor n module W and associate W to the ordered sequence x1 to xn. By this sentence, we mean that this VOA module has n copies of vertex VOA action, and each copy of V action is assigned with a marked point xi. So the order is important. So the definition of a conformal block is like this. A conformal block is a linear map phi from W to C, which is invariant under the action of V and X on W. This definition is originally due to Zhu and Frankel-Benz V, but it is a little different from their definition because we associate a V tensor n module to the ordered sequence. They associate each V module to each marked point. The space of conformal blocks is denoted by this symbol CBXW, and we usually draw the picture like this throughout my talk. This is the Riemann surface, and it has some local coordinates, and you associate a V tensor n module to the local coordinates, and this will be a vector space. This will be a finite dimensional vector space. The finite dimensional condition is guaranteed by the C2 cofinite condition. And the conformal block functor from the rep V tensor n to the finite dimensional vector space category is a left exact functor. It can be directly, it follows directly from the definition of the conformal block. Okay, our first dinatural transformation obtained from conformal blocks is called the sewing conformal blocks. Let x tilde be a n plus L pointed surface, and x be the sewing of x tilde along the L pairs of points. Of course, x tilde is possibly disconnected. Throughout my talk, I will use the blue color to represent the points not for sewing, and the red points are the points to be sewn. This color will help you memorize our points to be sewn and the points not to be sewn. You can see this picture. It has n marked points here, and it has L pairs of points here. It has n L points here, another L points here, and you saw these L pairs of points. to get a higher genus Riemann surface on the right-hand side. And on the conformal block level, you associate a V tensor at n level. You associate a V tensor n module W to the blue point here. For each V tensor L module X, you associate X to the one group of L points here, and another module, the conjugate module of X to the another group of L points here, and you solve this conformal block, and you will get a higher genus conformal block. Our theorem says that the sewing conformal block procedure will be convergent, and thus will give a well-defined linear map like this. And moreover, it is quite easy to check that if it is a well-defined linear map, then this sewing map is dinatural with respect to X. Okay, so in this theorem, the most important part is to prove the convergence. Just like the results obtained by Gui, we also found a linear differential equation to prove this result, to prove this convergence result. Okay, so it is a dinatural transformation, but we expect this is not only a dinatural transformation, it will give us a coend. That is, you can write this conformal block space as the integral of the conformal block space on the left-hand side.
I have a question, Hao. Do you use this?
Okay.
Do you use the C2 cofiniteness to deduce the differential equations, or do you just need C2 cofiniteness to get the braided tensor category structure and the rigidity?
Yes, I use C2 cofinite condition to obtain the differential equation, and this is perhaps the most important part to use the C2 cofinite condition. The differential equation, most important part is higher genus differential equation is guaranteed by the C2 cofinite condition.
I see, but do you expect that you could weaken it to C1 cofinite?
C1 cofinite works fine when you consider genus 0 case, but it is higher genus. I don't think we can get a weaker condition.
Okay, thank you.
Okay, you're welcome. Okay. As I mentioned just now, we expect Sx to be a coend, but it fails to be a coend by Miyamoto's observation. Let me explain this in details. It is quite easy to check that any dinatural transformation into this category. This category is the finite dimensional vector space category. Must be surjective in order to be a coend. However, if you for fixed V tensor n module W, S fails to be surjective in the case of self-sewing, and it fails to be a coend. This is due to Miyamoto's observation. Miyamoto considered a three-pointed sphere, and so one pair of the marked points to get a torus from the sphere. And they say that Miyamoto says that this sewing map with respect to this picture is no longer surjective. And Miyamoto used some notation called the pseudo traces to solve the problem. Since it is no longer surjective, it should consist of contains some traces other than the ordinary trace, and it is called the pseudo traces. So by adding pseudo traces in the genus 1 conformal block space, it will be a surjective. It will be a surjective map. Another approach to solve the problem is called the left-exact coend. Left-exact coend is usually studied by the TQFT people. This is a method which is quite similar to pseudo traces, because these two methods are introduced to solve the same problem observed by Miyamoto. Okay, pseudo traces are studied by VOA people, for example, Arak, Fiordalizi, Huang, and Miyamoto. And to give a suitable formulation of modular invariance, they add the pseudo traces into their genus 1 conformal block space in order to make this space a modular invariant space. And roughly speaking, pseudo traces is a generalization of single sewing. In this talk, I will mainly focus on coends, so I will spend some time to introduce lefty Z coend. So for simplicity, in the following 3 pages, I will assume L equal to 1 for simplicity. And in this case, X will be a V module. Recall that we already introduced Lyubashenko's coend. So TQFT people use the dinatural transformation of L to induce a family of morphism like this. This is a morphism between 2 home spaces. And the definition is quite simple. This family of morphism is denoted also by Sx, but it has different S. This is mass frac X, and the S with respect to the sewing is denoted as Masco X. They are different right here. Okay, this is a family of morphism in this category. This category is the category of left exact contravariant functor from rep V tensor N to the finite dimensional vector space category. And it is easy to see that this Sx is also dinatural with respect to X. But they can prove that as a coend, as a dinatural transformation in this category, the left exact contravariant functor category, it becomes a coend. This is proved by Lyubashenko and Fuchs and Schweiger. Assume that V is strongly finite and the rigidity conjecture is true. This Sx is a coend in the left exact contravariant functor category. That is, it induces the following equivalence. This equivalence is in the left exact contravariant functor category. And this equivalence is some substitution of some kind of pseudo traces in TQFT sense. Although I formulated their theorem in VOA context, they actually proved this theorem in a categorical sense. That is, they start with some with the data of a finite tensor category and proved everything in the categorical sense. But I can formulate their results in the VOA context. So I assume this condition. I will show later in my talk that this home space is equivalent to this conformal block space. And this home space is equivalent to this conformal block space. So it is natural to guess that this equivalence can be translated into conformal block language. So this is my conjecture. This is our conjecture. On the other hand, we recall that our sewing map gives a dinatural transformation from this functor to this functor. This functor are left exact contravariant functor defined by conformal block. Assume that our conjecture says, as if we assume that V is strongly finite and rep V is rigid, through the equivalence between home and the conformal block, our sewing map, this Sx coincides with the mass frac Sx defined in the categorical sense. If this Sx actually coincides with this X, this Sx, then our sewing conformal block dimensional transformation will become a coend in the left exact contravariant functor space, and you can the sewing map will induce the equivalence in this category. Okay, this is our conjecture. The main problem of this conjecture is this thing, the relationship between two SX. Okay, this is the left exact coend. Actually, we can solve this problem with another approach that is called the disjoint sewing. And with the help of disjoint sewing, we can prove that the dimensional transformation defined by sewing conformal blocks is a coend in the vector space category, the finite dimensional vector space category. So in order to describe the geometric data of disjoint sewing, I use this page. Let X be a n plus L pointed surface. This is X. Y be a L plus K pointed surface. This is Y. And the color is really good for you to memorize which points are to be sewn. This is L points, and this is another L points. So you sew these L pairs of points to get a higher genus Riemann surface on the right hand side. This Riemann surface is a n plus k pointed surface. You fix a V tensor n module W and associate this W to these blue points, and another V tensor K module M, and associate this M to this blue points. Then every blue point has its module. By our previous discussion, we can apply our sewing conformal block theorem to this case, also to this case, since we never assume that the conformal block we start with, the Riemann surface we start with is connected. So we choose two connected component, and we get this result. We can also say that the sewing conformal block map is a dimensional transformation in the finite dimensional vector space category, defined like this. Okay, our main theorem can be stated as the integration formula. This is called the sewing-factorization theorem A. It says that Sx is a coend in the vector space category, and you can write the formula here as an integration formula. So this is called the sewing-factorization theorem A because there is another theorem B which is equivalent to A, and sometimes B is more useful and sometimes A is more useful. So I introduce them all. And this builds a relationship between the lower genus conformal block and the higher genus conformal block. If you assume V is in addition, if V is in addition rational, then this result is mainly due to Gui and Damiolini, Gibney, and Tarasca. And they prove this result in the rational setting. And in our paper, we generalized this result to the non-rational setting. Okay, in order to introduce our formulation of sewing-factorization theorem B, I introduced a notion called the higher genus dual fusion product and higher genus fusion product. By this result, this result is due to 3 people, but I forgot to write their name here. But this result is an algebraic result. It says any left-exact functor from a finite C linear category to the vector space category is representable. Since our conformal block functor is left-exact, so we can find a V-tensor L module denoted as a diffusion XW, such that there is an equivalence of the contravariant functor here. So through the equivalence of contravariant functor, you can identify this home space with this conformal block space in a really natural way. If you choose X to be this V-tensor L module, then you can consider the identity map in this home space. Then through the isomorphism of the contravariant functor, you can find omega X in this conformal block space. And this is called the canonical conformal block. And the conjugate module of the diffusion XW is denoted as fusion XW, and this is called the homogeneous fusion product. And this construction is quite vague, but we have an explicit construction of diffusion XW as a subspace of the full dual space of W. And this construction can be found in GZ1. And our proof of sewing-factorization theorem relies heavily on this construction. And I want to say more about this. This subspace, the definition of this subspace is really similar to a notion called PZ compatibility in Huang-Lepkowski-Zhang's paper. And we use the as an analog of PZ compatibility to define the vector space of this. And we use a notion called propagation to define the module structure of this module. And the construction is really useful. And we must use this construction to prove our main result. I will demonstrate this result in the next page. Okay, recall that we have already get the omega x. The omega x is in this conformal block space. You can see this. By sewing the omega x with any conformal block on the left-hand side, you can get a conformal block on the right-hand side by the convergence of sewing. Our sewing-factorization theorem says that it is not only a well-defined map, it is an isomorphism of the vector space. And the isomorphism is given by the sewing of the canonical conformal block. And this also builds a relationship between the higher genus conformal block and the lower genus conformal block. You can simply memorize this sewing-factorization theorem by seeing the higher genus picture. And I draw some parts of the higher genus Riemann surface by the green part. And you can replace the green part by some kind of fusion product. And it will not change the isomorphism class. And the isomorphism will be given by the canonical conformal block with respect to this fusion product and diffusion product. And you can reduce the genus by replacing some parts by the fusion product. This is a folklore. Okay, this is our sewing-factorization B. And I will prove that the sewing-factorization A and sewing-factorization B are indeed equivalent. And the equivalence is given by a theorem given by Lyubashenko and Fuchs and Schweiger. They prove that the family of linear map from this to this is actually coend with respect to X. And the linear map is given by this formula, as you can see. By their result and the universal property or the definition of diffusion product here, you can easily prove the equivalence of sewing-factorization A and sewing-factorization B. So in order to get both of them, you will only prove one of them. Okay, this proves the equivalence of sewing-factorization theorem. In the rest of my talk, I will give some applications of sewing-factorization theorem. The first, this is indeed an application of the diffusion product, but I also write it here. This is called the geometric realization of Liu-Ba-Shenko's end and coend. Write P as a genus zeroth sphere with 2 incoming points and 1 outgoing points, and another sphere called Q with 1 incoming points and 2 outgoing points. By our fusion product and diffusion product construction, you will first get fusion P. This will be a functor from rep V tensor V to rep V. Because you associate any module here, then you will get a fusion product and diffusion product coming out of the blue points or blue circles. And this functor is simply the fusion product defined by Huang-Lipovsky Zhang. Actually, they defined the fusion product from rep V times rep V to rep V as a bifunctor. But Robert McCrae proved a remarkable result that the lim product of 2 rep V is equivalent to the category rep V tensor V. So our fusion product coincides with the lift of Huang-Lipovsky Zhang's fusion product functor. Another construction is from Q. Q, you will have fusion Q and diffusion Q. This will assign each VOA module, each V module to a rep V tensor V module. This will be the module coming from the red points here. Okay, this is our theorem relating the Liu-Ba-Shenko's coend with our diffusion product. It says if you assign the vacant module here to this functor, you will get diffusion QV, and this bimodule, this V tensor V module is exactly this diffusion product, or is this coend. The coend given by the tensor product over C. This is a bifunctor. If you apply the fusion P functor, you can move the fusion product into the integral because the fusion product commutes with any colimit. So you can remove, or you can move your fusion product into the co-integral, and you will get the next formula. And this builds the relationship between Liu-Ba-Shenko's coend and our diffusion product and fusion product construction. In particular, this theorem implies the existence of Liu-Ba-Shenko's coend in the representation category of V without assuming rigidity. As I said in the beginning of my talk, Liu-Ba-Shenko's coend can be you can prove the existence of Liu-Ba-Shenko's coend if your category is rigid, but this result can also prove the existence without assuming the rigidity. And if your VOA is semi-simple, you can replace this integral by the direct sum over all irreducible modules. You can also consider the dinatural transformation of the coend we have already described before. By the definition of diffusion product and the propagation of conformal block, you will have this isomorphism. The first isomorphism is given by propagation. You will remove the vacant input module, and you will get this isomorphism is isomorphic to the conformal block space. The second isomorphism is given by the definition of diffusion product. And through this isomorphism, you can identify the identity of X with some kind of morphism in this home space. And this morphism is denoted by iota X. This is a morphism in rep V tensor V. If you this will correspond to the diagonal transformation of this diffusion QV as a coend. If you apply the bifunctor fusion P to this functor or to this morphism, you will get a new morphism. We also denote this morphism as iota X. This will be a morphism in rep V, and it will become the diagonal transformation of this V module as a coend. This is our description of diagonal transformation. And with the help of these results, we can get a connection of our conformal block space with the topological modular functor. Recall that we have these two genus zero sphere. By our sewing-factorization theorem, you can consider the fusion product of V over some genus zero or genus one torus. And by our sewing-factorization theorem, we can say that if you consider this fusion product, it amounts to say that you first apply the fusion Q to this vacant module V, and you get a bifunctor, and you assign the fusion P, then you will get a V module, and this will give you an isomorphism of V modules by our sewing-factorization theorem. And from now on, we assume that our VOA is strongly finite and our VOA category is rigid. We assume this because we find this formula really similar to one of our formula we obtained just now. So we want to say that we want to prove that this is self-due under some condition, and we can prove this module as a V tensor V module is self-due under the condition of strongly finite and rigid. We proved it is self-due with the help of the existence of a non-zero modified trace. And recall that we have this coend, and this coend is really similar to this fusion product. And if we have this equivalence, then our fusion product of the vacant module V over some genus one torus is equivalent to the Liu-Ba-Shen-Ho's coend. This is our result under the assumption of a strongly finite condition and a rigidity condition. And with the help of this equivalence, we can obtain another main result in this talk. Let X be an n-pointed surface with genus G, and associate a V tensor n module W to the points of X. If our VOA is strongly finite and our representation category is rigid, well, we have the isomorphism between the conformal block space and the home space involving the Liu-Ba-Shen-Ho's coend. The proof is quite simple. If you already have the sewing-factorization theorem, you only have to write the X and W as like this. Each handle body is represents a genus. It is some parts. You can use the propagation to assign a vacant module to each handle. And using our sewing-factorization theorem, you can replace each handle with a fusion product. And we already get an equivalence of the Liu-Ba-Shen-Ho's coend and this fusion product of the vacant module over the torus. then you will get this isomorphism. This isomorphism is given by the sewing-factorization theorem. Then you reduce all genus of this higher genus surface to a genus zero sphere. This is quite good because you can easily describe a genus one or a genus zero conformal block. Then you can identify the genus zero conformal block with the home space on the right hand side. So we start with a vertex operator algebra and use our vertex operator algebra to define the space of conformal block. And at the end of the day, we can say that this space of conformal block is equivalent to the home space, which is the topological modular functor considered by the TQFT people. Of course, we have to assume the rigidity conjecture. And if you only care about genus one torus, I can write our result here. Also, we assume that our VOA is strongly finite and our representation category is rigid. We choose a VOA module W and associate this W to the point of the torus. Then by our previous result, we will have the following isomorphism given by the sewing-factorization theorem. And on the left hand side, it is the space of conformal block. On the right hand side, it is quite categorical. And in TQFT people, they may use the Liu-Ba-Shenko's coend to define the categorical S transformation. And on the left hand side, VOA people may use some analog of conformal block to define the modular S transformation. Of course, there may be some pseudo traces in it. But our result is the first to relate torus conformal block and Liu-Ba-Shenko's coend in the VOA context. And before our work, no previous work on the modular invariance has succeeded in establishing such relation. And this relation will be crucial to relate the modular S transformation and the categorical transformation. The modular transformation is here and the categorical S transformation is here. And so we hope there will be further progress and further applications of the sewing-factorization theorem and some topological modular functor description by our conformal block theory. And this is all for my talk. Thank you so much for listening to my talk.
Thank you so much, Hao. Let me stop the recording and we can move on to questions. Thank you for the wonderful talk.
Okay, thank you.